begin looking at Einstein and how his vision of light helped modify the world as to what light was and the consequences of the speed of light. So we got to start off by looking at where light comes from, and it really comes from the core of stars. It all begins with light, and light is born in the nuclear furnaces within the cores of stars. And we have this matter that was, let's just say, gravity took over and kind of pulled it all together. It's dominated by hydrogen and helium, and therefore within the core of stars, this is where we have some unique features taking place. This is where heavier elements are created, and this is where the pure conversion of matter comes into play into generating tremendous amounts of energy. So this takes place in the core of stars, what we call thermonuclear fusion. And we can see that the atomic mass units, if I have 4 hydrogen that go into creating a helium atom, that the math doesn't make sense. And we essentially see that the difference between the matter, right, the m in this equation, energy equals mass times the speed of light squared, the matter is converted into pure energy that we view as sunlight. And so this kind of talks you through that. But the missing mass is actually the conversion into pure energy. And this is the sunlight. This is what's driving processes on the Earth. So here we can take a look. I want you to watch the video. This is a cool video on coronal mass ejections. And this is an explanation of how nuclear fusion takes place. You can watch these on your own time. But essentially, now that we have sunlight, we can take a look at the consequences as to what that means for the universe. The speed of light is the speed limit of the universe. Every part of the electromagnetic spectrum is pure energy traveling at c, the speed of light. That the speed of light, though, has some very interesting consequences. So here's some factoids. Nothing travels faster than the speed of light, 186,282 miles per second, and it's the letter C. Not even gravity can travel faster. Matter and energy are really the same thing. They're just organized differently. So energy equals mass times the speed of light squared. Energy and matter are not only related, they are kind of one and the same. It only takes a tiny amount of matter to be converted into a tremendous amount of energy. And lastly, the sun is continually providing the Earth with energy, combining hydrogen into helium. So there we see energy converted directly from matter. And the sun has been around for about 4.55 billion years, and it's got another 4.5 to 5 billion years left in it. So we got plenty of time to sort that out. So here we can look at where Einstein kind of jumps right in. It's important to make sure you understand what frames of reference are. And you can watch this video on your own. I think a lot of these videos are between, say, 2 and 5 minutes. But here's what it's saying. If these two people, I guess, are kind of jumping off this cliff, tossing a ball back and forth. I know it's kind of a funky scenario. But these frames of reference between the blue and the red person, they're going to view it as the ball going side to side. Whereas somebody observing this from outside their frame of reference, they're going to see that ball traveling in these parabolic shapes. So from different reference frames, there can never be agreement on the simultaneity of events. Meaning, from an observer outside the frame of reference, compared to that of a person in the frame of reference being observed, they see and experience something different. However, both are correct. And that's important here. So we do a little activity in class. It's actually a form of Galilean physics. It's a classical physics. This is not involving speeds at the speed of light. But they add together. So if we have somebody traveling on this little cart with wheels and they toss a ball, that the velocity of the ball compared to the outsider, the observer, sees the total velocities added together. That this here would be 20 meters per second. So if she's moving at 10 meters per second and she tosses the ball at 10 meters per second, an outside observer sees the ball traveling at 20 meters per second. But if we were to ask her how fast she sees the ball traveling, remember, she's traveling at 10 meters per second. She only views the ball moving at 10 meters per second. And this is where relativistic physics comes into play. It's very unique once we start looking at a flashlight. That if she's moving, and we can say she's still moving at 10 meters per second, and she shines a flashlight on, the flashlight is still traveling at the speed of light. Nothing happens with the speed of light from either frame of reference. So if she's stopped, the photons leaving the flashlight are traveling at the speed of light. And if she's moving, the photons are traveling at the speed of light to somebody inside the frame of reference or somebody outside the frame of reference. That the speed of light, no matter what frame of reference you're in, the speed of light is constant. And that's a key part of this. So we can apply this concept to gravity. Gravity obeys the speed of light. So we could say that gravity is not instantaneous. It also travels at the speed of light. If the sun were to burn out, we wouldn't know it until about 500 seconds after it occurred. And that's the time in which it also takes for photons or light to reach us through space. And at that moment, the Earth would continue traveling in a straight line, since no force, no gravity would be keeping us in orbit. So we would travel in the direction we were last heading. So you can watch this video here. This is on Brian Greene's, oops, didn't mean to click on that. It's from a Brian Greene video of, I'm not really sure which one this one is, but anyway, the video is perfect because it gets into the space-time curvature. I just don't remember what this particular video was on. So when I kind of follow that once more, just get through the concept of it. Oh, Elegant Universe, by the way, was the video here. Kind of lost me for a second. So if the sun were to burn out, gravity would be traveling. The Earth wouldn't know that gravity was gone until the light that was traveling with the gravitational waves traveled with it. So it would take 500 seconds, just as it takes 500 seconds for light to reach us, so too would gravity. Nothing travels faster than the speed of light. And as a consequence, something has to give. So if you watch this video, you'll see that it talks about this light clock that kind of ticks and talks, and it's 1 second from the tick to from the oscillation of the light beam. And so what happens is that, light is the fourth dimension. And that if you travel faster through space, you travel slower through time. And you might say, well, how does that happen? Well, if you follow the light clock analogy, it has to travel a greater distance. So the clock itself actually slows down. And you'll want to watch this video and pay attention to what's going on. It's actually very well done. But you can actually, your biological clock, if you're within here, within the fast-moving spaceship, you age differently from being inside the frame of reference than somebody who is outside the frame of reference. Very important there. So time, mass, and space all change as a result of c, or the speed of light. Strange things occur. Time runs slower the faster one travels through space. Notice if you're moving, clock goes slower than somebody outside. Mass increases for an object that approaches the speed of light. That you actually get a change here, that traveling at or near the speed of light, this 1,000 kilogram object would actually increase in its mass. And space contracts in the direction an object is traveling. If it's not moving, it's this size, and if it is moving, it contracts in the direction it's traveling. That this result is that only the speed of light is constant in the universe. Time, mass, and space are relative. And you can go ahead and watch this video here, once again on relativity a little bit more. So we can apply that to this really unique storyline of what's called the twin paradox. We can calculate the time on the rocket compared to a person's time on Earth. And it's essentially like saying that the rocket ship is going to be approaching the speed of light. And you can pause this and relook at the math here. But essentially it's saying this. One twin gets in the rocket and the other twin stays on Earth, and they're both 23 years old. Here the astronaut twin goes near the speed of light for 2 years of her time, of her life. In 2030, she returns. The astronaut returns only 2 years older, but her brother is 20 years older. Simply by traveling at near the speed of light, her clock that's on board with her is ticking at a different rate than somebody on Earth. So therefore they age differently. And the effect is enormous for speeds approaching that of the speed of light. So if you're traveling at 99% the speed of light, then you're only going to be aging at 14% of the time on Earth. So if somebody left and returned 100 Earth years later, they would have only aged 14 years by their biological clock. So that concludes special relativity. Now we're going to look at general relativity. And this is where things get a little bit messier. We're simply saying that space-time is four-dimensional. And the more massive an object, the more the space-time is curved. And gravity travels at the speed of light. And gravity is what holds objects in orbit, right? Two masses at a distance are can be gravitationally bound to one another. So here's where things get a little funky. That the more massive, the more it curves the space-time fabric. So the theories of special and general relativity erroneously appear to be about the same topic. Special relativity is about motion and how measurements are changed if we change the point of view from the observer. General relativity is about gravity, or about the interactions of masses with one another. The reason why Einstein called generalization of the other is that special relativity deals with uniform motion, whereas general relativity is valid for any type of motion, accelerated or not, and is therefore a more general theory. So Here's an interesting phrase I want to make sure you understand. That space-time tells matter how to move. Matter tells space-time how to curve. So let's apply that to a couple pictures. That the sun, very, very massive, it curves its space-time around it. And the Earth, because it has, let's just say it's in motion, it has inertia, it's simply following this wave, this gravitational wave of the curved space-time around the sun. That a more massive object is going to affect the space-time around it even more. That the sun bends the space-time significantly more than the Earth. Notice that the sun keeps the Earth in orbit as Earth follows the space-time curvature, the same way that Earth keeps the moon in orbit. Or they're really kind of playing off of each other's space-time curvature, and the gravitational field is just saying that the moon is moving around and following this path that has been curved in the space-time fabric. And therefore, straight lines are the paths of the photons. They follow the space-time curvature. Therefore, straight lines in space actually curve. So when you look out at the night sky and you see that star in the distance, it might actually be behind the sun or behind another object. However, because it follows the curvature of space-time, we view it, where we observe it isn't necessarily where it actually is. There's your finality in general relativity.